So thanks. So this is a joint work with Gérard Verfaillie on time-dependent simple temporal networks, and this work was published in a Journal of the Operations Research Community in 2013. So the motivation for this work is that in some domains there is a need to model activities whose duration is time-dependent. What it means is that we may have activities, as here, and the duration of these activities depend on the time at which these activities start. For instance, here, depending on whether the activity starts at time 1, 3, or 8, the duration is 4 units of times, or 6 units of times, or 3 units of times. And this happens, for instance, in logistics, where you have a transfer time between locations, which can depend on traffic congestion, or in a production planning, where the duration of a task can depend on the resources currently available. And we want to deal with such problems. But the issue is that standard simple temporal networks techniques are not usable anymore to model such problems, because in STN, we can only model constraints of this form, y minus x greater than a certain constant. So y and x are time points, and we want to impose a distance, a minimum distance, which must be constant between time points. So what we do in this journal paper is that we introduce a framework for managing a more general class of temporal constraints. And more precisely, we introduce TSTN. The T stands for time dependent. A TSTN being defined by a finite set of time points, as in STN, and a finite set of constraints, which are more general than STN's constraints. We impose constraints of the form y minus x greater than a function of x and y. And this function is called the minimum distance function to be satisfied between time points x and y. And the novelty is that this minimum distance function depends on the time at which the time points occur. The only assumption that we make on this function, on this minimum distance function, is a kind of monotonicity, which say that the sooner an activity starts, the sooner it must end. For instance, such schemes are not allowed. We cannot, by starting the task later, finish it earlier. We do not consider minimum distance function which would violate this assumption. We could end the task exactly at the same time or after, but not strictly before. And mathematically, it corresponds to a monotonicity of this function. So there is a formal definition for that. On this basis, it is possible to extend standard definition on STN to time-dependent STN. For instance, the notion of solution. A solution will be an assignment of time points satisfying all the temporal constraints. We can extend the notion of consistency, the notion of distance graph. The distance graph is a graph in which you have one node per time point and one arc per temporal constraint. The difference with STN is that here, in the case of time-dependent STN, the labels of arc are not necessarily constant. They are functions. But we can extend these basic definitions. Now, one fundamental question is, can standard results on STN be extended to time-dependent STN? And to answer this question, the first step is to define how to reason about a single temporal constraint. So in STN, in standard STN, when you have a constraint like this, y minus x greater than d, you use what is called domain reduction rules by saying that if you have this constraint, the minimum value in the domain of x may have an influence on the minimum value of time point y, and similarly, the maximum value in the domain of y may have an influence over the maximum value in the domain of x. And these domain reduction rules are illustrated here on the figure on the right. In TSTN, we can generalize these rules by saying that if we have a constraint y minus x greater than the minimum distance function between x and y, as in STN, the minimum value of x may influence the minimum value of y, and the maximum value of y here may influence the maximum value of x. And these rules, instead of using these equations, we use, for the first rule, what is called the earliest arrival function. It is illustrated here on the right. If we start the transition from x to y at the minimum possible value for x, we can compute the earliest time in the domain of time point y such that the temporal constraint is satisfied. And similarly, on the other way, we can compute, given a value in the domain of time point y, we can compute the maximum possible value in the domain of x, which satisfies the temporal constraints. And using these two rules, we can prune some parts of the domain of time points. These two functions, these earliest arrival function and latest departure functions, can be computed using iterative techniques, interpolation techniques, because they correspond somehow to find a zero of a function, and we have techniques to do that. And in some cases, as in STN, we can directly write an analytical formulation for these two functions. So this was how to reason on a single constraint in the time-dependent STN framework. The good news is that, similarly to STN, if all constraints are made locally consistent using these rules, that is, if we apply these rules over all constraints until reaching a fixed point, then the earliest schedule and the latest schedule are solutions of the TSTN. This means that if you assign all time points to their minimum values or all time points to their maximum value, then you have an assignment which satisfies all the temporal constraints. The bad news is that, contrarily to STN, non-extremal values, that is values in the middle of the domains of time points, are not necessarily globally consistent. This means that they cannot necessarily be extended to a solution. Here is an example. This is a time-dependent STN with two constraints, two temporal constraints. Here, the minimum distance function depends only on x, and we suppose that it has this shape. It can be shown that if we propagate the temporal constraints for this TSTN, we will prune the domain of x and the domain of y, and we will end up with this state. So here, assigning x and y with their minimum values will give an assignment which satisfies both constraints, and assigning x and y to their maximum value will give an assignment satisfying also both constraints. But if we take a value in the middle of the domain, in the middle of the domain of x, for value 10, for instance, it could be shown that this value is not globally consistent. That is, it cannot be extended to a solution of the TSTN. The reason for this is that if we start the transition from x to y at time 10, we have to pay 15 units of time, so we can end the transition only at time 25, and this is not consistent with the second constraint, which imposes that the distance between x and y must be less than 10. But we can give sufficient conditions so that we have the global consistency of non-extremal values. For instance, if you consider the distance graph, and if you only have simple temporal constraints in cycles of the distance graph, then you are ensured, it is sure that non-extremal values can also be extended to solutions. So we can obtain again the one of the good results available on STN. On this basis, we define algorithms for TSTN. So we adapted and extended existing techniques for STN, published by several authors. So what we do is that we maintain at each step lists of constraints to be propagated, to be revised, and we propagate the constraints until the lists are empty. We have techniques which are defined in the paper for managing incrementally constraint additions and removals. We also have techniques to minimize the number of constraint revisions. We build a decomposition of the distance graph into strongly connected components, and this allows us to order constraint revisions This point is important because in TSTN, revising one constraint using the earliest arrival and latest departure function, it's more costly than in STN. So it is useful to minimize the number of constraint revisions. And last, we perform inconsistency detection based on the detection of propagation cycles, as in STN. For instance, here, if the minimum value of y has an influence of the minimum value of x, and if the mean value of x has an influence on the minimum value of z, and if the minimum value of z has an influence over the minimum value of y, we obtain a propagation cycle. And in STN, in standard STN, we are guaranteed that when there is such a cycle, the STN is inconsistent. The bad news is that in TSTN, this is not necessarily true. The inconsistency is not equivalent to the existence of a propagation cycle. The reason for this is that in TSTN, in time-dependent STN, when you traverse a propagation cycle again and again, the propagation cycle can become less negative, and you may prune your domains. You may converge to a state in which you traverse the cycle, but you obtain no more pruning. In the journal paper, we define some sufficient conditions which allow for the equivalence to hold again. For instance, if there are only simple temporal constraints in cycles of the distance graph, then we have the equivalence between inconsistency and the existence of a propagation cycle. And last, if we have this equivalence, it is possible to show that we obtain the same bounds as in STN. That is, we can propagate temporal constraints in a number of constraint revision, which is proportional to the number of time points times the number of variables, of constraints. In practice, TSTN techniques are implemented in the in-cell solver presented at ICAPS last year, which is a constraint-based local search library. And we used TSTN several times in the space domain for managing time-dependent constraints for Earth-observing satellites. For instance, for these satellites, we may have time-dependent durations for transition between two acquisition activities of the satellite, because the satellite is moving on its orbit, the Earth is rotating on itself, and we have time-dependent aspects. Or on such problems, we may have time-dependent duration for download activities. So it's useful in practice. And the last slide is about the perspective. There already exists some extensions of STN, such as STN with uncertainty, STN with preferences, STN with preferences and uncertainty. And we could try to time-dependentify all this framework. And that's it.
Any questions?
So thank you. I had a question regarding slide 9, I believe. It was about, this problem, the graph, the next one you showed, the graph. So there's a problem here you cannot necessarily, or there's a problem with the consistency now in TSTN, TSTN. And the problem here is that this distance can take a value of 15, and that would not be consistent with the other constraints.
Yes.
So isn't there, maybe this example is a bit simple or something, but isn't this prunable? You can you have these two constraints, so you can restrict the distance to at most 10, and then you'll never have this problem. Or
if you want to prune values in the middle of domains, then you have to decompose domains, and this introduces additional problems. One choice which we made is that we wanted to manage only simple intervals for time points. We did not want to obtain disjoint intervals, because then in terms of complexity, you don't have the same guarantees. And yes, that's it.
Okay, we have time for another question. Okay.
So maybe I can complete the answer if there is no more question. Another point is that here, an important point is that there is a difference between the monotonicity of this function, because here it's not monotonic, and the assumption, this one, the monotonicity of this function. What we assume is only the monotonicity of this function and not of the other one.
Okay, well, I'll ask a question. So I like using these things in planners. Supposing I wanted to make the time between X and Y depend on some other variable Z.
Yes.
Would that be possible, or is that a huge
Z
extension?
being a time point, or Z
Yeah,
being
Z is some other time point. Yes,
we did not do that. We only consider binary constraints between time points.
Uh-huh.
But in what we do in our constraint-based library, you can have a Z, which is another parameter, but not a time point.
Okay, so it could be something other than the time point. Okay, let's thank the speaker then.